scientists from Nanyang Technological University, Singapore, NTU Singapore, and the California Institute of Technology, Caltech, United States, have developed a new type of chainmail fabric that is flexible like cloth but can stiffen on demand. The lightweight fabric is 3D printed from nylon plastic polymers and comprises hollow octahedrons, a shape with 8 equal triangular faces that interlock with each other. When the soft fabric is wrapped within a flexible plastic envelope and vacuum packed, it turns into a rigid structure that is 25 times stiffer or harder to bend than when relaxed. The physical principle behind it is called jamming transition, similar to the stiffening behavior in vacuum-packed bags of rice or beans. Known as wearable structured fabrics, the development could pave the way for next-generation smart fabrics that can harden to protect a user against an impact or when additional load-bearing capacity is needed. Potential applications may include bulletproof or stab-proof vests, configurable medical support for the elderly, and protective exoskeletons for high-impact sports or workplaces like construction sites. Published in the journal Nature, this interdisciplinary research results from a collaboration between experts in mechanical engineering and advanced manufacturing. The researchers said that their research has fundamental significance as well as industrial relevance and that it could lead to a new platform technology with applications in medical and robotic systems that can benefit society. An example from popular culture would be Batman's cap in the 2005 movie Batman Begins, which is generally flexible but can be made rigid at will when the capped crusader needs it as a glider. The scientific concepts behind the variable stiffness fabric is called jamming transition. This is a transition in which aggregates of solid particles switch from a fluid-like soft state to a solid-like rigid state with a slight increase in packing density. However, typical solid particles are usually too heavy and do not provide enough tensile resistance for wearable applications. In their research, the authors designed structured particles where each particle is made of hollow frames in the shape of rings, ovals, squares, cubes, pyramids, and different shapes of octahedrons that are then interlocked together. These structures, known as topologically interlocked structures, can then be formed into chainmail fabric that has a low density and yet high tensile stiffness using state-of-the-art 3D printing technology to print them as a single piece. They then modeled the number of average contact points per particle and how much each structure will bend in response to the amount of stress applied. The team discovered that by customizing the particle shape, there was a trade-off between how much weight the particles will have versus how much the fabric can bend and how to balance the two factors. To add a way of controlling the stiffness of the fabric, the team encapsulated the chainmail fabric in a flexible plastic envelope and compacted the fabrics using a vacuum, which applies pressure from the outside. The vacuum pressure increases the packing density of the fabric, causing each particle to have more contact with its neighbors, resulting for the octahedron-based fabric in a structure that is 25 times more rigid. When formed into a flat table-shaped structure and vacuum locked in place, the fabric could hold a load of 1.5 kilograms, more than 50 times the fabric's own weight. In another experiment, the team dropped a small steel ball, 30 grams measuring 1.27 centimeter in diameter, onto the chainmail at 3 meters per second. The impact deformed the fabric by up to 26 mm when it was relaxed, but by only 3 mm when it was stiffened, a 6 times reduction in penetration depth. To show the possibilities of their fabric concept using different source material, the team 3D printed the chainmail using aluminum and demonstrated that it has the same flexibility and soft performance as nylon when relaxed, and yet it could also be jammed into structures that are much stiffer compared to nylon due to aluminum's higher stiffness and strength. These metallic chainmails could be used in applications such as body armor, where they must protect against hard and high-speed impacts from sharp objects. In such a case, the encapsulation or envelope material could be made from aramid fibers, commonly known as Kevlar, used as a fabric in bulletproof vests. Moving forward, the team is looking to improve the material and fabric performance of the chainmail and to explore more methods of stiffening it, such as through magnetism, electricity, or temperature.